Hello! In this video, we will take a look at the Wavetable synthesis project from Chapter 2 of Sound and Music Projects for Eurorack and Beyond. This is another introductory project, so if you're new to programming and electronics, this is a good one to experiment with. It's simple, but yet there are a lot of opportunities to experiment with the code and add additional potentiometers and things of that nature. So let's have a look at the circuit first. This project illustrates the use of two potentiometers. These particular types of potentiometers are sometimes called trim pots, and they are a good choice for breadboarding because larger potentiometers, you'd have to solder leads or find another way to connect them to the holes on the breadboard. So these are pretty nice for breadboarding a prototype. To talk about how the power works for this, we have USB power that's powering the Teensy microcontroller. The Teensy microcontroller has a 3.3 volt regulator that's powering this top rail, and then we have ground that's connected to this bottom rail. One thing that's important to note, and I mentioned in the previous video, is that whenever you are reading from a potentiometer on the Teensy, you want to make sure that you're connecting the 3.3 volt, which I am, to both of these potentiometers, and not the 5 volts that is coming from USB, because that will damage your device. These pins are not tolerant for anything over 3.3 volts. So in terms of the hookup of the potentiometers, we have 3.3 volt going to one side of the pot. The other side connects to ground. So I have this hookup wire going to the ground rail. And then the middle lead or pin of that potentiometer goes to one of the analog inputs. And on this example, analog 0 will be for the attack, and analog 1 will be for the release. In terms of source code, you will want to visit the audio system design tool that's available at PJRC, the company that makes the Teensy microcontrollers. And I have an example here that's used for this project. One thing that I'm doing that's a little different today is I'm using a PT8211 digital analog converter. And that's a kit that's available from PJRC. It's a good kit if you only need audio output. If for most readers, I would recommend the Teensy Audio Shield, which provides input and output. But for today's demonstration, that will be, I think, a good and very simple object to look at. Incidentally, if you wanted to rewire this for the audio shield, it would be a simple matter of finding the output section. So here we are. We're going to use I squared C, and then you would find the control, which is this, and these are the two objects that are used with the traditional Teensy shield. You notice there's a little error message showing up because now we have two DACs that are fighting one another. So in any case, that's all outlined in the book, and either approach will work well. In terms of the setup, we have the wavetable oscillator going to an envelope, and I would point your attention to this description of the envelope here, and these are the functions of that object that we will be calling in code. Particularly for this example, the attack and release, which are all take a parameter in milliseconds. I have that running to a mixer. This is optional, but it's something that I'm in the habit of doing, and then it's sending the output right to the PT. PT8211. And again, with the I2S option, the only change would be hooking that up to the different object. Just a reminder that you can click export and copy this code into your project, and you're good to go with instances of all these objects. Let's take a look in the Arduino IDE, and you'll see those objects that were created by that online tool. One thing to point your attention to for wavetable synthesis is that we use an array of samples, and I describe a process for creating your own samples in the appendix of the book. But I would note that there are some pre-configured libraries that are available of some samples that you can use that are available in the Teensy source files. So here we have a file, strings samples.h, and essentially what this code does is it creates an instance of an audio synth wavetable object, and it points us to the strings that are contained in this sample file here. And so just note that this word strings, this is the instance of that wavetable. And when we go to the main code, you'll see that by including that, it copies all of those samples into memory inside of that object. And then using the wavetable set instrument function, that's where we really point to those samples. So once again, samples H sets that up. You don't really need to know the inner workings of C++ to be able to take advantage of this code. There's a file that contains the samples, and then we point to that here. Note also that there are two MIDI callback functions, one for note on and note off events, and I talk about that in detail in the book. It's quite simple to set up, but we'll take a brief look down here at the two functions that respond to incoming MIDI messages via USB. And then finally, the main part of the code are these two analog read functions. And I've given them the name knob1 and knob2, and those correspond to the potentiometers. The map function is a useful function that will help you to scale values. And keep in mind, in its default configuration, the Teensys and Arduinos read from the analog input, and the range of values is 0 to 1023. Has to do with the number of bits. And what these map functions do, the way I have them configured, is for knob 1, we take that range, expected range, and then map that to a new range. So what I had in mind is essentially from 0 to 4 seconds or 4,000 milliseconds. So it takes that variable knob and it scales that. And of course that could be done with some simple math as well if you want to hard code that, but the map function is convenient. So we have a new variable and for attack and release that's based on those map functions. And now getting back to the envelope object, and just a reminder, if we take a look here again, we have this envelope object. We have some functions that can be called, and if we go back to the source code, you'll see that that object is created right here, and that's something that we pasted in using the online tool. And then here's the point where we call those functions. And so what this does is enables us to contour the attack and release of this basic synthesizer. And of course, if you find this interesting and fun, you might want to add additional potentiometers that make a true ADSR envelope, but we're keeping it simple for today. Let's take a listen. I'll show you the configuration. I'm using Ableton. I just created a channel and I'm sending the output of the MIDI to the Teensy. And that's, again, I can't overstress how powerful this feature is of the Teensy microcontrollers, that they can function as autonomous USB MIDI devices and audio devices and interact with your DAW. For today, we're just doing that to get some notes into the Teensy, but it is really a powerful feature. So going back to the circuit here, I'm going to turn down the two potentiometers and play a note. And so you can hear it's a string sample, but not a particularly successful one, mostly because the attack is rather awkward. So let's add a nice fade in on that. And you can hear how much more musically expressive that is. Let's add some release as well. The Wavetable project is simple, but also powerful, and it shows how easy it is to take advantage of the power of the Teensy audio library. To just review that process, you would start by creating the primary objects using the audio design tool at pjrc.com. In our case, we just had a wavetable oscillator, an envelope, a mixer, and then an output device, which could be the Teensy audio shield, or in this case, the PT8211 DAC. And through some simple circuitry, in this case, two potentiometers, we were able to put a voltage into the analog inputs on the microcontroller, read those voltages, and use those potentiometers to change the parameters of the envelope. So again, pretty simple stuff, but something that you could expand very easily by, for example, adding additional potentiometers to control other parameters such as filter cutoff if you want to add a filter, or adding a sustain and decay components of that envelope device. So there are a lot of ways to expand and build on this project without necessarily having to have a deep level of programming knowledge. So much of the code is handled by the powerful Teensy library. So I hope you found that fun and interesting.